Okay, so what I want to do in this video is just to highlight and review this document that I've made available to you called Preparation of Calibration Curves. This is done by a company whose job it is to go around to laboratories sometime and to professionally train their employees, or to at least kind of review and help them remember what to do and what not to do in a lab. So the turnover rate can change depending on the company, or a company might have an influx of new employees that have to go through some training exercises and programs before they're turned loose. And companies like this can go out and help those burdens that might happen with a laboratory and a new employee staff. Okay, so the preparation of the calibration curve, it says a guide to best practice, and it was published in 2003, but honestly, a lot of the things have not changed here. The reason that I want to cover this is because I think that it is a very good job summing up some of the common problems that happen in a laboratory and how to fix them. So it says valid analytical measurement, VAM. It says the work described in the report was supported under a contract with the Department of Trade and Industry as part of the National Measurement System Valid Analytical Measurement Program. And it gives you a better insight about some of the problems that they discovered when they went into a lab and started talking about laboratory employees and how they made standards and how they made calibration curves. And then eventually how to fix those mistakes. So it starts off with an introduction, and it gives you an idea of what the calibration curve is. And hopefully, if you're watching this video, you now know what a calibration curve is because we've talked about it so much. So typically on the x-axis, that's your concentration. It says milligram per liter. That's the -1 up there. It means the dividing sign. So mg/L is what that would translate to, and that's part per million. And then the instrument response up here on the y-axis, it's arbitrary. That comes from the instrument itself, and it could be transmission, it could be absorbance, it could be area, it could be just an arbitrary unit number such as percentage. Who knows what it would be, but that's the response. So that's typically the setup of the calibration curve, and you can read through these paragraphs and kind of get more details about the descriptions in the paragraphs that they are talking about and that they're listing for you to read. If I keep scrolling on, it says that they begin to study these people in a lab environment, and they break them out into groups, and they allow the groups to kind of prepare their own standards and run their own samples, and then generate a calibration curve. And then they looked at this data and kind of stepped back and said, okay, what's wrong? What could have improved here? So it talks about the calibration process, and it says there's a number of stages, and we've talked about these really. Plan the experiment. So what calibration curves do you need? What concentrations do you need? What kind of samples are basically being given to the lab? What concentrations will those be on average? And it says make the measurements, plot the results, so make the calibration curve. Carry out regression analysis. Does it make a line? Can you get your linear regression line? Can you solve for that? Then it says evaluate the results. So the results that you get from the samples, can you plug those into the regression line and solve for the concentration? And then estimate the uncertainty associated with the test samples. This is in the world of statistics, and we're not really going to talk about that section. We've touched on it a little bit as far as confidence intervals go and standard deviations and that type of thing throughout the program, but that's not the purpose of this lecture. This lecture is to focus on the calibration curve, and that's it. And then under 2.1, it says these are the things that you need to do. You need to figure out the number of calibration standards, right? Do you use 3? Do you use 5? Do you use 7? What's the concentration of each of the calibration standards? So where should the group of them be? And you should go a little bit higher and a little bit below or after that. The number of replicates at each concentration, right? So do you run them just one time and make your calibration curve? Or do you run each one of them twice or each one of them 3 times and do an average? And then how are you going to prepare the calibration standard? What are you going to be using? What's the process going to be like? Hopefully you'll stay away from serial dilutions. We've talked about that, right? And hopefully you'll start with a primary standard that has been certified, and you make your standards based off of that primary one. So it says for an initial assessment of the calibration function as part of method validation, for example, standards with at least 7 different concentrations, which include a blank, should be prepared. So that means the blank is going to be 1, and then I've got 6 other standards that I have made in a laboratory. That's just basically what they are encouraging you as a laboratory to do. The standard concentration should cover at least the range of concentrations for the test samples. And this one says and be evenly spaced across the range. Ideally, the calibration range should be established so that the majority of the test sample concentrations fall in the center of the range. As discussed in section 2.7, this is the area of the calibration range where the uncertainty is at the minimum. It's also useful to make at least dupe measurements at each concentration, particularly at the method validation stage, because it allows you insight into the precision of the equipment. Making replicates on the same calibration standard gives partial information about the variability, as it only covers the precision of the instrument. It does not include the preparation, which means you, right? We're only testing the instrument when we do that. So that's a little bit of their suggestions to a laboratory. These are the things that you probably would want to do, and we're listing them out for you. The matrix is used to prepare the standards requires careful consideration. It is sufficient to prepare the standards in a pure solvent, or does the matrix need to be closely matched to that of the test samples? And that really depends on what you want to achieve and what you want to accomplish. So we've talked about the problem with the matrix. We've talked about some of the things that we need to watch out for when we choose them, especially when we begin to analyze our blank. It talks about an internal standard. We've not talked about that. We will in the course, but that's not the purpose of this particular module lecture. It's just generating a calibration curve. It says, ideally, the standards should be independent. They should not be prepared from a common stock solution. Any error in the preparation of the stock solution will propagate throughout the other standards, leading to bias. You don't want that to happen. A procedure sometimes used in the preparation of calibration standards is to prepare the most concentrated standard and then dilute it by 50% to get the next one. And then that one's diluted by 50 to get the next one, and so on. It says this procedure is not recommended. In addition to the lack of independence, the standard concentrations will not be evenly spaced across the concentration range, leading to the problem of leverage. That's serial dilution. They're telling you not to do it. Here it says construction of the cal curve using 7 standards can be time-consuming and expensive. Remember, they pay you for your time. The more and quicker that you can process samples, the better off the company's going to be, because they don't have to waste money paying you to do the same job over and over and over. If there's no doubt about the linearity of the calibration function, but there is a known bias, like a non-zero, it says a 2-point calibration may be used. In this case, 2 calibration standards are prepared with concentrations that encompass the likely range of concentrations for the test samples. This is in very limited circumstances with very simple pieces of equipment. We never really do 2 calibrations for a complex multi-thousand-dollar piece of equipment. These would be things like sometimes your ISE probes, your ion selective electrodes, such as pH probes, fluoride probes, chloride probes, soil moisture probes. Very simplistic in nature. Those are 2 points and those are okay. We don't need 7 buffers to make my pH probe work properly. All right, so I'm going to let you read this document all the way through, and parts of the assignment that you will see will come from this document that I would like for you to read. I'll tell you the sections that I would like for you to play the most focus on, but what I want to do is scroll to the very end of this document, and they begin to sum up the analysis. And I think that this summary will also do us well, or good as well. right? So here are their conclusions that they've made. And it says the benchmarking exercise highlighted a number of problems when carrying out instrument calibration curves. And some of the pitfalls include the following. Number one, the concentration range covered by the calibration standards does not adequately cover the range in the test samples. So we've talked about that now, right? We've said that my standards go up to a certain point and go down to a certain point. If my samples are higher or lower than those values, then I cannot reliably report those numbers. I either have to dilute them if they're too high and run them again, or redo a calibration curve and incorporate a higher standard to include that sample. And if they're too low, then that's a problem as well. I have to basically say it's lower than the MRL. So next, the concentrations of the calibration standards are not evenly spaced across the calibration range. So this is going to be basically the majority of them, right? We want the majority of the standards in the center, the average value that we're seeing with our samples. And then we said we're going to pick out a couple below and a couple above. But the majority of the standards should be smack dab in the center. So that's basically what that's referring to. The ones that are the most important critical standards of the bunch need to be evenly spaced. 2, 3, 4. And then I can have one that's down at 0.5, and then maybe one that's up at 5 or 6. And then that will be a proper range for my calibration standards. Remember, the closer your standards are to each other, the more reliable that the line is in that range. Next, the uncertainty associated with the concentrations of the cal standards is too large. That basically means that you're not prepping them the right way, right? So these are really tiny little bitty amounts, like 0.1 milliliter that you need to deliver to make the standard with. That's not reliable. You don't probably feel comfortable with that, right? Or if you have really large volumes that you have to take care of, then that can be a problem as well, working with that amount of solution. Make sure that you pick and judge the preparation properly. You don't want it too small. You don't want it too big. You want workable volumes and measurements that you can utilize in a laboratory easily. The next one, it says the wrong regression is carried out. Regression of X on Y rather than Y on X. So that basically means you're getting your axes flipped. Concentration should always go on the X. Signal should always go on the Y. They found out that people like to flip those axes. Don't flip them. Something else with wrong regression, you're not picking a linear regression. It should be linear regression almost every time in a laboratory, but we've talked about all of these other options as well that are out there that could be used, but in a laboratory, linear is preferred. It says the calibration line is fitted through 0 when the intercept is in fact different from 0. So this is almost going back to that 0 shift. You never want to do that. If your blank is not reading 0, then do not put 0 in for that blank and plot it on the calibration curve. No one said the calibration curve has to go through 0.00 exactly, so don't force it to do it if it's not going to do it. The instrument software used to carry out the regression and automatically calculate the concentration, but a plot of the calibration is not obtained. So that basically means, do you know how to operate the system? Do you know how to operate the software? We want you to utilize the technology to its extreme, right? If the machine can give you a standard calibration curve, then let the instrument give you a calibration curve. But be able to go in and print off calibration data. Be able to go in and print off a report that shows what the signals were based on the concentrations that you made. You have to have a physical trail of this in most instances. And if you don't know how to print off that paper, if you don't know how to go into the software and set all of that up and double check the concentrations and double check the absorbances or the signals or the areas, then you're doing us no good. Next, the residual standard deviation is used as an estimate of the uncertainty. This is really statistics, and I told you we're not going to be focused on that. The next one, the performance of the instrument used to make the measurements is not within specification. This was the whole concept of doing dupes, right? Standard 1 and then standard 1 dupe. You want to make sure that those signals are coming back to you with the same values. And it says in order to alleviate some of the problems above, these are things that you need to do. 1, plan the calibration study so that you know for sure the concentration range is included in the samples. Include a standard with a 0 analyte concentration, so that means a blank. Never forget that, always run it. Ensure that appropriate materials and apparatus are used to prepare the calibration standards. So if you're doing really small volumes, make sure you're using micropipettes. If you're doing large volumes, make sure you have appropriate volumetric glassware to do them with. Next, ensure that the instrument used to make the measurements is fit for its purpose, right? So don't be using the wrong instrument to analyze these samples when it's not going to do you any good. Next, plot and examine the results. Don't just take everything for granted. When the machine gives you a number, don't just turn in that number, write it down, and say, this is what the machine gave me. Do you really physically, mentally understand how you got that data and how that data was generated in the software? If you had to do it on your own, could you do it on your own without the help of the piece of equipment? Next, use validated software to perform the linear regression. That means don't use these third-party, cheap, skanky little software platforms. Typically, the go-to is Excel. Sorry, people, it's not Google Sheets. If you're going to be using software in a laboratory, most of the time it's going to be Excel or something similar that's a sister to Excel. Next, do not set the intercept to 0 unless there's evidence that the intercept is not statistically different from 0. So again, that goes back to 0 shift. Don't do it. Finally, plot and examine the residuals. That goes back to statistics, so we're not really going to be worried about that in this video module. And the next one, calculate the uncertainty for the concentrations predicted by the cal line. So do you know how to mentally and physically go in, run a sample, obtain a measurement, plug it into a regression curve on your own, and come up with a concentration? Believe it or not, some people don't know how to do it. They rely on the equipment and they rely on the instrument to do it every single time for them. That's not a good lab worker, that's a monkey. I can train a monkey to go into a lab and do the same process over and over and over, right? I mean, if they can learn sign language, they can learn how to operate a pH meter. So what I'm saying to you is don't take everything for granted. Really fully understand where these numbers are coming from, what the machine is doing, what the software is doing for you. So that way you can at least talk the game when someone says, what's the problem? What's going on here? Or tell me about what you're doing today. That could be a coworker, it could be a manager, it could be an auditor. Make sure that you make yourself look good when you're presented with those types of questions. So some of the assignment information will come from this document. So my advice, maybe not print it out, but just go through and read it and then make some notes. And I'll tell you which sections to basically focus on the most. That way you can really place a focus on it, take notes in those sections, and know that those are basically going to be asked in the upcoming assignment.